Hi, welcome to our poster presentation. For the summer, we did summer research on the Hyers-Ulam stability of equations on discrete and continuous timescales. The people that worked on this were A.J. Jensen, Cole Montplaisir, and Dr. Anderson. And for the introduction on what the project is, we examined the Hyers-Ulam stability on specific first-order complex, constant, coefficient dynamic equations. So it's x delta is equal to lambda x of t on the timescale of p alpha h, which consists of continuous intervals of length alpha greater than 0 and discrete jumps of h greater than 0. Moving on to our definition of what a timescale actually is. So in this project, we considered a specific timescale t, which displays both the discrete and continuous pieces of our project, mentioned previously as h and alpha, respectively, where the timescale is closed subset of the real line r. In this case, let t equal p sub alpha h for step sizes of alpha and h, assuming they're greater than 0. Then our function is p sub alpha h is equal to 0 alpha, and then union with alpha plus h and alpha plus h plus alpha. And then we just keep doing union along with it. So we just keep adding on pieces of continuous and then jump over the incontinuous part and just keep adding on those pieces to get a more full picture of our graph.
In our specific case, we are considering the the exponential function e sub alpha h of t, which can be defined as seen as e sub lambda from t to 0 is equal to 1 plus h lambda to the k times e to the lambda times t minus hk for all t in that interval of continuity. And when lambda is in the complex numbers. We call this an exponential function because it does actually satisfy the equation that x to the delta t, which is using our differential operator, which we will explain later, and is equal to lambda times x of t. It can also be rewritten for all j in 0 to alpha, which does make it a little easier to do some of our math down the road, which we will make use of. And we can also rewrite our lambda function using r and I, which then allows for all on the interval of negative pi to pi, which then allows us to employ the W Lambert function, which is a unique little function we found, which helps a lot with the complex cases, which again, we will discuss in a little bit. So our differential operator specifically, we had to combine two timescales because normally discrete and continuous do not work well together. So we actually defined a new differential operator. And for this, we use continuous differentiation where it could be evaluated continuously and discrete on its discrete parts. So we defined that differential operator as x delta, which then for all t in that continuous interval, we just, again, did continuous differentiation like you normally would in calculus. And then we use the definition of the derivative for the endpoints or over those jump gaps and those discontinuous portions. And due to the nature of this, we also had to define a quote forward jump operator as sigma, which for that we said it is equal to t for all t in that continuous interval. And then when t is going to break that continuous interval, we add on our jump factor of h to put it back inside of a continuous variable. That way we're always acting on an area where we actually can differentiate. And then that brings us to Hyers-Ulam stability, which it formally says that you are given an epsilon greater than 0 and suppose a function phi exists such that phi prime minus lambda phi is less than epsilon. And then, which is basically saying that you take your differentiated equation minus its answer and that they should be within a small margin of error of each other. And then we suppose there exists a solution of our equation, which we did prove before, with lambda in complex and t in our time scale, such that our function minus a perturbed version of that same function is within k epsilon of itself, or of each other, excuse me. And then we would say that if that k exists greater than 0, then the equation is Hyers-Ulam stable at that point with the constant k. In our project, we set x of t equal to x naught, which would be our starting point, times our exponential function. And in general, then, when we convert that into the phi for our full equation, we would have that as phi of t is equal to phi naught times our exponential function plus our exponential function times the integral from t to 0 of q of s over our exponential function at sigma. And then that is, of course, differentiated over s. And then for our stipulation with q of s is we have to assume that it is less than epsilon, otherwise this whole thing doesn't work. And yeah, and then basically what this whole big mess of a definition is saying is that if you take our original exponential function and you perturb it or add on a small margin of error, and then subtract it from itself, if it's Hyers-Ulam stable, they will remain close to each other as we take the limit of these equations. And when they are not Hyers-Ulam stable, they will diverge from each other when we take the limit as it approaches infinity.
Moving on to what the W-Lambert function is, or how we use the W-Lambert function. Throughout this project, we employed a thing called the W-Lambert function, which is denoted by W sub z, which satisfies W sub z of y e to the power of W sub z of y is equal to y for any z in the real numbers,
The integers.
the integer. This imposes some interesting new problems for our exponential function, particularly where h is greater than or equal to alpha over w sub 0 e to the negative 1. And moving on to these graphs that we have here, on the left side, or the left graph, some of the key points that make up this graph are, this is our graph when h is equal to 1 and alpha is equal to 1. And the black line that is in the center there is where our r is equal to 1. The blue dot that you see in the center is our hole in the graph. And then the red line is where our bifurcation value is and where it touches and then goes back out. And the left graph is just a more zoomed in version of the graph on the right. The graph on the right pieces together more points just so you can get a more full picture of the graph. And moving on to the base of exponentials to find bifurcation values. So on the first graph there, we have when h is less than alpha over w sub 0 e to the negative 1. And there we have just one unstable point in the graph. The second one is when h moves on to be equal to that value. And as you can see, it touches the dotted line there, which represents our another unstable point. So that increases our unstable points to 2. And when we move on to when h is greater than the value, it crosses over that dotted line twice, causing our unstable points to be 3 now.
But we have gone over the definitions of everything and given you an introduction to our problem, we can go on to the actual findings of our research this summer. So first, we examine the Hyers-Ulam stability when our lambda value is in the real numbers. And here we come out with 3 cases when we observed our function. And we did have some idea where these would go to based on previous research that had done by Dr. Anderson and his colleagues, which observed the Hyers-Ulam stability of a specific exponential function when on continuous and discrete separate timescales, but not necessarily combined together. And you can kind of take those and get an idea of where it's going. So first, when lambda is equal to 0, we do not have Hyers-Ulam stability for any k, which was to be expected. And then when we take that lambda value and put it from -1 over h, our step value, to infinity and exclude 0, we do actually come with Hyers-Ulam stability with a pretty good k value of 1 over absolute lambda. And then in a third case, we do have when we observe lambda is less than -1 over our step value, and we have 0 is less than h less than alpha over the W Lambert function of e to the -1. We do have Hyers-Ulam stability with k equal to -1 over lambda times this big fraction here, which is e to the alpha lambda times 1 plus h lambda minus 1 plus 2h lambda over 1 plus e to the alpha lambda times 1 plus h lambda. Now, it is worth noting too that these are the best k values you can get, because there are any k larger than this will suffice. So we did also do some testing and research to make sure that we did come out with the least k value that would still hold for Hyers-Ulam stability. Then we move into a special case, which is where we still keep lambda in the real numbers, and we fix our h value to be strictly at the bifurcation value that we mentioned before. And when we do this, we also must note that our exponential function here is then equal to -1. And then we also must note that lambda is equal to -1 when we have lambda is equal to negative alpha minus the W Lambert function of e to the -1 over alpha. Now, if we take our lambda and we observe it from the negative W Lambert function at e to the 1 over alpha minus 0, and to infinity, excluding 0, we do find that we have Hyers-Ulam stability with that same constant as in case 2 above, which was to be expected. We do then observe that when we have lambda equal to 0 and lambda at that value, which makes our exponential function equal -1, we do not have Hyers-Ulam stability, which is basically reaffirming what this picture told us down here, that when this drops down and touches that bifurcation value where we expected to have instability, we do in fact have instability. And then we go on and find that when we take our lambda and put it in everywhere, that is not including our bifurcation, or when our lambda makes our exponential function equal that bifurcation value, or equal -1, we do have Hyers-Ulam stability with that same constant again as above, which is to be expected. So then, what happens when we take our lambda in R and then we fix h to be strictly larger than that bifurcation value, or in this case here where we are past that bifurcation value. Here we again must say that we found that our exponential function would be less than -1, which is the new information we would be gaining at lambda sub -1, which is equal to -1 over h plus 1 over alpha times the W Lambert function at that value that we have lambda at of negative alpha over h times e to the alpha over h. And similarly, we find the same thing for lambda naught when we take 1 over alpha and the W Lambert function of that same thing at the naught function of the W Lambert function. So first, we find that when we keep lambda in that same interval as, again, from negative 1 over h to infinity, not including 0, or from this value here on, we do find that we, again, have Hyers-Ulam stability with k equal to 1 over absolute lambda. When we take and we push the lambda value to be between, or to be strictly equal to those points where it crosses this -1 line, we find, as to be expected, that we do not have Hyers-Ulam stability. And again, when we find that when we say that we want our value to be at any point from here to here, or that is past this first 1 over h and not at our instability points, we find that we have Hyers-Ulam stability again with the same constant as before. So then we wanted to move on from the real numbers and examine Hyers-Ulam stability in the complex numbers. So for that, we found that there were 3 general cases. So first, when we have r equal to 1, we do not have any Hyers-Ulam stability for any k. And then for case 2, we have r greater than 1, in which we actually come out to have 2 specific points of k due to the nature that the real part of lambda could be equal to 0 or not equal to 0, since at the real part of lambda equal to 0, we did not have Hyers-Ulam stability before. So we actually found that when it is equal to 0, it is fairly easy with a k value of r of h plus alpha over r minus 1. And when we move outside that real part of lambda equal to 0, so when it's not equal to 0, it actually can vary. So that is when we would take the max of j, which is basically our partial platform, and then we take that and we came out to find our function as 1 minus e to the j real part of lambda minus r plus r to the e, or r times e to the negative alpha real part of lambda plus j real part of lambda minus h e j to the real part of lambda divided by the real part of lambda times 1 minus r. And then again, we did find Hyers-Ulam stability when we have 0 is less than r, or when r is between 0 and 1, with k equal to negative k, when we observe k as the part to b here, which is that same large function I just read off. And then we wanted to give a specific example of instability, because the stability is pretty easy to recognize, but how do we know that something is unstable? So when we have lambda equals 0, we expect instability, and then we have to find a specific phi which proves that it is unstable. So when lambda is equal to 0, we can use phi of t is equal to epsilon t to test for that Hyers-Ulam stability. So first, we have to verify that that phi can actually be used. So we plug that phi into our differential operator and make sure that it is equal to, that it can be derived in both ways, in which we come up as epsilon for both continuous and discrete parts. And then we can take that phi that we now proved can be used for Hyers-Ulam stability, and we plug it into our function for Hyers-Ulam stability. And since we know that phi is equal to epsilon minus t, and because lambda is equal to 0, we know that our exponential function is equal to 1. So therefore, we can say that our function is equal to the absolute value of epsilon t minus x naught, which if you take the limit as x not or as x approaches infinity, we will find that it approaches infinity because, or as t approaches infinity, sorry, t grows and x naught is fixed, so that no k will be able to bring these close to each other.
Okay, moving on to our real world examples, how we could actually use this in, or an easier way to think about this. So imagine there's an AC unit on during the summer, and there's times when it will work and be turned on, and times when it'll be turned off. That is how you can think about the continuous and discontinuous or discrete variables. So in our example, our time that it's off and on are set to a specific time. And you can change that before you start, but you have to specify that when you start it. And then for our research that we have done, this is purely theoretical. We haven't tested anything on actual applications for the real world yet, but we set the framework down so that people can use it if the time arises that it will be applicable. And then for the end of this, we looked into the nabla operator, which is opposite of delta. So basically it flips the graph around completely. So our graphs would just be flipped, but keep the same important points and bifurcations.
And then we would also like to give a specific acknowledgement to the Centennial Scholars Grant through Concordia College and the Centennial Scholars Endowment donors, which made it possible for us to do this research this summer. Thank you.